All right, today we're jumping into a high-stakes rescue mission. We're going deep, deep into the world of production web scraping, where just one tiny architectural flaw can cause a complete, system-wide meltdown. Our mission? Figure out why this failure happens, and then architect a system that can actually survive the chaos of the real internet. Let's get started.
So, you've built a scraper. And hey, it's elegant. You run it on your own machine, you hit a simple route, and it works flawlessly. Every single request comes back with clean, perfectly structured data. It feels like a perfect launch, right? But then you deploy it. A real user sends a request. The little spinner on their screen just keeps spinning, and then, boom, 504 Gateway Timeout. Total mission failure.
So what the heck happened? Your monitoring dashboards are just screaming at you. RAM usage has shot through the roof, the API is frozen solid, and the entire application has gone down. And the cause? It was all because of one single, slow-loading website that your scraper was trying to hit.
Okay, so what went so wrong with our initial design? Let's analyze the flawed blueprint that led us straight into this disaster. The mistake is, it's pretty simple, but it is absolutely deadly in production. You're mixing ingestion with execution. You're asking one single process to do two totally different jobs at the exact same time. This slide just lays out the whole chain reaction of failure perfectly. Our web server, we'll say it's built with Flask, is trying to do everything all at once. You can see the flow right here. It accepts the request, then it has to launch a browser, scrape the site, parse the data. It's all one linear blocking process. And that means one slow site equals one blocked worker. Get enough of those, and your whole API is toast.
And here's the thing you've got to understand. This isn't about you writing bad code. Your scraping logic could be a work of art. The problem is the architecture. It's just broken. It's a design that is fundamentally not built to survive the wild, unpredictable nature of the web. So, how do we fix it? Well, we need a completely new blueprint, a new design. Let's call it the Mothership Architecture. The fix is all about one powerful idea: decoupling. We have to separate the part of our system that talks to the user, that's our control plane, from the parts that do all the heavy, unpredictable work. Those are our execution units. Now, in this new architecture, Flask becomes our mothership. Its only job is to receive the request and immediately respond with a 202 mission accepted status. It doesn't scrape a thing, it doesn't wait. Its job is to be fast and responsive, period. So once the mission is accepted, the mothership doesn't do the work itself. Nope. Instead, it just pushes a tiny, lightweight task message, just the URL and maybe some parameters, into Redis. Think of Redis as our super fast communications relay, our message queue. And this is where the real magic happens. We use a task queue system called Celery to create a whole fleet of autonomous drones. These are workers running completely separately from our Flask API. They're just sitting there, constantly listening to that Redis queue. They pick up tasks, launch browsers, scrape pages, and they handle all the slow websites, completely outside of the user's request cycle. And this just shows you the night and day difference. Our old monolithic probe, it was slow, impossible to scale, and super fragile. One little failure could bring the whole thing crashing down. But the decoupled fleet, it's instantly responsive, you can scale it to the moon, and it's incredibly fault-tolerant. If one drone crashes trying to scrape some horrible website, who cares? The mothership and the rest of the fleet are totally unaffected. This new architecture isn't just about being reliable, it's also about being able to scale massively. So let's talk about how we can scale up our drone fleet for basically any mission imaginable. The scaling strategy becomes just so simple. Need more scraping power? Easy. Just launch more Celery workers, more drones. What if you need to avoid getting blocked by a specific website? No problem. You can create totally separate queues for different domains, each with its own fleet of drones and its own specific rate limits. This gives you incredibly fine-grained control over your whole operation. So the bottom line is you get the absolute best of both worlds. Your API that your users interact with, it stays lightning fast, which means a great user experience. Meanwhile, your scraping operation in the background becomes horizontally scalable, capable of handling thousands of tasks without even breaking a sweat. Now that our architecture is solid, we need to lay down some ground rules. Think of these as our mission-critical protocols.
These are the rules that will ensure the long-term success and health of our data gathering operations. And this right here, this is the single most important rule you have to remember. Redis is for messages, not data. Let me say that again. Redis is for lightweight messages. If you start trying to cram huge chunks of HTML or big JSON files back into Redis, you're just rebuilding the exact same bottleneck in a different part of your system. So here's your commander's checklist. First, scraped results should go directly from the Celery drones to a proper data store, like a database or object storage, like S3. Second, validate everything. Use a data validation library like Pydantic to define a strict schema for your data. That way, no bad data ever gets into your system. And third, optimize your serialization. For any APIs that serve this data, you should replace Flask's default JSON tool with a high-performance one like OrJSON. You'll get like a 5 to 10x speed boost. It's wild.
And all of this brings us to our final, ultimate takeaway. Look, getting a scraper to work once on your machine, that's the easy part. But production-level scraping, the kind that runs reliably day in and day out, that's not about clever CSS selectors or fighting the latest anti-bot tech. It is all about robust, resilient system architecture. So I'll leave you with this question to think about for your own projects. Is your scraper a fragile, disposable probe destined to fail under real-world pressure, or are you building a resilient, decoupled fleet that's actually designed for the long haul? Because that choice of architecture, that's the difference between mission success and mission failure.